Okay, please, Robert.
Okay, thank you very much, Jaslav. It's a great pleasure to be in Vienna again, even though it's only virtually. I hope that at some point in the future I could come in person, actually. But so now that the pandemic is receding, maybe the next visit could be in person. Okay, so let me share the screen. Okay, so you should see this now. So yes, Jaslav already said, so this talk will be about the positive formalism. And I want to focus in particular on one example, which is black hole to white hole transition. I'll say more later about this example. And so one thing I would like to say first is that please feel free to interrupt me, because I would really like to be able to transmit these things to you in a way that you can really understand and follow. And so if there are doubts or question that something is not clear, then please interrupt me. Okay, so in this talk, so the main reference is below here. It's a relatively long article about the positive formalism. Some things I'll say today are not in this article, many things in fact. Some are in other articles, and some are not, haven't appeared in print yet. So in this talk, I want to start with a short overview what the positive formalism is about. Probably many of you know already some things about it. I will not in this talk spend time to derive the positive formalism from first principles. That's for other occasions. But instead, I want to focus on an application to a concrete example. And the other focus of this talk will be to explain in more detail how it is related to the standard formulation of quantum theory. Okay, so first, the positive formalism is an axiomatic framework for formulating physical theories. In particular, it accommodates different branches of physics, such as classical statistical mechanics, the standard formulation of quantum theory, quantum field theory, but also generalized probabilistic theories. It also provides a timeless formulation of quantum theory. So this is where it's really interesting to you in particular. And one of the main motivations behind it is that the idea is also that this could provide a basis for the formulation of a quantum theory of gravity. So one thing I should make very clear, if I say that the positive formalism accommodates these different frameworks, it doesn't mean that, for example, when I say quantum field theory, it doesn't mean that the positive formalism contains the standard model. So it doesn't encompass these fields of physics in a way that it describes all their contents, but it's only a very basic framework for these different areas. In the same way that if we think about quantum theory, we can say, well, quantum theory are some axioms where you have Hilbert spaces, you have operators, and you have certain rules to talk about measurements and probabilities for measurement outcomes. In the very same way, you should think about the positive formalism. It's just a framework that specifies axiomatically some basic ingredient for any theory, and it tells you how you can combine these ingredients and how you can use them to make probabilistic predictions about measurements. So that's what this is about. There are different versions of the positive formalism. There's a version which I denote here just with PF, which is just the basic ingredients. So these different frameworks of different areas of physics, they from the point of view of the positive formalism arise when you add more structure to this basic positive formalism. And I will say a little bit more about these additional structures. So additional structure can mean just that, an additional structure. It can also mean that you impose additional conditions or additional axioms. But I'll say a little bit more about this later. So from a conceptual perspective, what is the positive formalism about? So here I have a picture that sometimes I like to show at the beginning of talks about the positive formalism, which is a picture where you can see it comes from a page that explains how the human vision works. So you can see an eye here. You can see an object, in this case a tree, and the light that comes from the tree, where it is focused onto the retina in the eye, and their electrical impulses go to the interior of the brain, where an image of this object, the tree, is reconstructed. So I use this picture here to explain the different focus that the positive formalism has compared to many traditional approaches to the natural sciences. So the kind of traditional point of view in let's say natural philosophy is that well, you perceive the natural world around you. You see all these objects and what is happening there, and so your focus is in understanding what these objects are, like the tree in this case, classify, organize them, and find the laws that govern their behavior. Now, in the positive formalism, the starting point is different, is taking as the primary ingredient not the object here, which is the tree, but the perception of the object, or the observation, if you wish. So it starts by thinking that you don't really know that there's a tree a priori. What you have is primarily you have a perception or an observation of the tree. So you have in your eyes like a detector which emits certain signals that correspond to observations that you're making, and then these observations are what you really have as the primary material, which you then in your brain use to reconstruct some object, or more generally, in the positive formalism, the starting point is to say that these observations are really the primary ingredients of the formalism. And if there's some object out there that generates these observations or not, that's a secondary layer or step in talking about the natural world. The primary one is the observation itself. And I should add to this also interventions. And so what this is about is classifying, organizing them and their results. Now this is, I mean, on the transparency, it looks like there's a contrast of the positive formalism to anything else. But of course, that's not the case. What this perspective of the positive formalism is really about taking serious what we've learned with the quantum revolution, with the revolution that overthrew classical physics, more or less 100 years ago, and where we understood that to understand the microscopic world, the physics of the microscopic world, we have to overthrow classical physics. And as you know, in quantum theory, the notion of observer plays a privileged role. And I would like to rephrase this slightly, and instead of observer, talk about the observation, but the essence is the same. The observation is the primary ingredient, is primary entity of should be a primary entity of the formalism, and is so really in quantum theory. So the positive formalism just takes this what we've learned from quantum theory seriously and puts it up front and first very explicitly. So mathematically speaking, the most important object in the positive formalism are partially ordered vector spaces. So these are vector spaces which at the same time are partially ordered sets. So if you take two vectors, then you might have a notion that one is less or equal than the other. And this notion is compatible with the vector space structures with addition and scalar multiplication. Now, between partially ordered vector spaces, the natural notion of map is that of a positive map. So these are linear maps that at the same time are required to map positive elements to positive elements. Positive meaning that the element is larger or equal to 0 in the partial order to the 0 element, which is the, oops, sorry. There's also a special element often, which is called an order unit. And what's special about such an element is that if you take an arbitrary element in the partially ordered vector space, then you can blow up this order unit by multiplying it with a positive scalar so that it becomes larger or equal than the vector space element that you started with. Another important ingredient is an inner product. You all know what's a positive definite inner product. Here, this is on the real vector space. And also, this has to be compatible with the partial order structure. So if you put in two vector space elements that are both positive, then the result has to be positive. So the main examples are examples that you are very familiar with, everybody of you. And the point is that, as I alluded to already, so the positive formalism as such may describe both classical and quantum physical models. And the difference lies in the different types of partially ordered vector spaces that enter. So in classical models, the partially ordered vector space is a space of real valued functions on a set. More precisely, in classical physics, these sets are things like the phase space of your model. And so the structure is the real valued function on phase space. And the physical interpretation of these is these are statistical distributions on your phase space. And there also comes the positivity. A function is positive if it has a positive value at every point, right? Or more precisely, a non-negative value at every point. And of course, to be a statistical distribution, it has to have exactly that property, right? Now, the order unit, you can take it to be just a constant function with unit value. And the inner product is the L2 inner product. So you multiply functions and you integrate over the space, so, which means that this is really not just a set, but it also has a measure. Now, in the quantum theory, well, as you know, the basic object is a complex Hilbert space. And then the space of the partially ordered vector space is simply the space of self-adjoint operators on it, and where the notion of positive operator gives you the partial order, right? So an operator is larger or equal to another one if their difference is positive, okay? And of course, you're all very familiar with this space if we think of these as encoding the mixed states of a quantum system, right? Now, this order unit is the identity operator, and the inner product is taking the product of the operators and the trace. So that's the Hilbert-Schmidt inner product. Okay. Okay, so now again, back to the basics of the positive formalism. So as I said, we take the notion of observation and of intervention as a primary, and so we encode this with an object that we call a probe, which subsumes an experiment, a measurement, observation, preparation, and intervention. One important aspect here, so this notion of probe comes with already fixed outcomes or fixed settings. So if you have a measurement that can have different outcomes, then to each of these different outcomes corresponds a different probe. Okay. Now these probes form partially ordered vector spaces. There's also a notion of interface between probes. And so in principle, if you look at this picture with the probes, and so of course the different observations or interventions that you make in different probes that at the same in the same measurement process, let's say, they are related. And to formalize these relations, we can use interfaces that model that there's an explicit interaction, or you can think of this as a communication or information exchange between probes. So a line indicates that there's such a relation between two probes. And again, these interfaces carry partially ordered vector spaces. Now, the rationale behind introducing the interface is not so much that there's an interaction between the probes, which you could also have a priori between any pair of probes, but is also to limit where such an interaction takes place. Okay, so that you don't have a lot of probes and anyone is connected to anyone else, and that's very difficult to describe. And it turns out that there are only certain interactions possible, and you model this with these interfaces, these lines. And then while you need to mathematically specify these different objects, you can put labels on them. So here we have labels on the probes, M1, M2, M3, labels on these interfaces, sigma 1, 3, sigma 2, 3, and so on. Now a probe in classical physics, you can think of a probe, for example, as corresponding to a classical observable. That would be one type of probe. There would also be types of probes that would correspond to modifying the dynamics of your classical system. In the quantum theory, the notion of probe is very close to the notion of quantum operation. Okay, so that's a very useful thing to think about. Probes as quantum operations or processes. And the interfaces, you can, in let's say the standard formulation of quantum theory, for example, they correspond to systems, right? And carry state spaces. So these partially ordered vector spaces associated to these interfaces, you can think in that context correspond to state spaces. Now, okay, so with all these ingredients, the question, a key question is, of course, that we don't only want to say, okay, we can measure some things and there can be relations, but the key question in the end is how from that do we get to predictions? Okay, and in particular, these predictions are probabilistic predictions. So we're talking about probabilities. Now, so in the positive formalism, to talk about the probability for some measurement, some outcome, what you need is you need to specify, of course, probes and interfaces and so on, but you need to specify two versions of these always. Why? Because in one version, which is on the right-hand side here, you're saying, okay, what are, let's say, your measurement instruments and so on, how are they connected, and also some data, for example, about what's the exterior temperature in your laboratory, in which way have you switched this device. But what you do not specify here is what is the outcome of your measurement. So here, for example, this would be a switch. This would be a device that has just a light that can be red or can be green. And this is a pointer device that points to some, let's say, some voltage or whatever. So you specify all this. And then, so this is the information that you fix, what determines the experiment you're doing. And then on the left-hand side, you're asking for a particular outcome, okay? Which means that the pointer device, not just the pointer device, but a pointer device where the pointer points to a specific measurement, let's say 2 volts. And also this other device shows a green light. And it's not just sitting there, but you're looking at it and it shows a green light. So to specify, to be able to talk about the probability of some outcome, you have to specify always these two sides. And that has to do with the fact, as I said already, that a probe is not just saying, okay, there's a measurement device, but at the same time, I have to specify all the knob settings and outcomes. Although you will notice that on the right-hand side here, we have a probe for the measurement for this pointer device without indicating a pointer. What does it mean? It means that you have the pointer device there, but you're not looking at the point, so you don't know its position. What you do know is that the device is there and it's plugged in, okay? Which corresponds itself to a probe. So the probes also allow for incomplete knowledge. That's very crucial. Now, the point is that these diagrams, if they're closed diagrams, evaluate to real numbers. So the real numbers come about by some composition of these elements, which are vectors in these partially ordered vector spaces. So there's a notion of composition, and that if the diagram is closed, it gives you a real number. Now here we have 2 real numbers. So the other thing is that related to the positive structure, to the partial order structure, it is always the case that these numbers are not just real numbers, but they are non-negative numbers. And then, so the probability for this outcomes corresponds to the quotient between the two, between the diagram on the left and the one on the right, where you do not specify these measurement outcomes. And on the left, you do. So schematically, we have a quotient like this. And here on the right, I just gave some names to these devices. So I put some letters to have an expression that looks more like a mathematical expression here. Okay, I'll tell you more about this in a moment. So it's crucial for this so if you've noticed, we have of this pointer device, we have 2 versions. One version where there's no pointer indicated, and one where we do indicate a pointer. And so these are 2 vectors. So the probes are vectors in the same space of probes. So they are partially ordered. So in this case, the partial order is so that this, where you specify a range for the pointer, is less or equal than the one where you don't. And also you have something similar for this device that can show red or green light. The sum of these two possibilities is just the device without knowledge of which color is shown on the light. So it's in this structure of your partially ordered vector space, the sum of these two is this. And then there are some other devices that appear in the picture. And this partial order here, and of course SG is smaller and equal than S star because these are all non-negative. And this means precisely, if we go back to the previous picture, that this is less or equal than this, and this is less or equal than this. And the composition respects this because the composition is what I told you before is a positive map. So it respects this, which means that this whole expression, the whole expression for the left, the number that you get when you evaluate the diagram on the left is smaller or equal than the number you get for the picture on the right, which means that this quotient will be less or equal than 1 and also will be larger or equal to 0. So it will be a probability. Okay, so so much about the basics of the positive formalism. One more thing I want to tell you is related to applications in space-time, which the example that I'll talk about later will be related to. So if so real experiments happen in space-time, and so there's an interaction only in space-time if we divide space-time in regions. Then there can be an interaction only between, a direct interaction only between adjacent regions, right? Because an interaction has to be mediated by signals that travel between the different space-time locations that we want to interact. So that means that if we do this division, then we have to put interfaces only between probes that are in adjacent space-time regions. So in other words, these interfaces now are really in correspondence to these hypersurfaces, these pieces of hypersurfaces where two different regions meet. So, so that means that we can forget about this drawing these links explicitly because they will correspond precisely to these hypersurfaces. So instead of associating these partially ordered vector spaces that correspond to state spaces to links, we can associate them with hypersurfaces in this setting. And also, if you do this, space-time, in the space-time picture, there's a particular type of probe that becomes important because you can say, for example, well, in one of these space-time regions, I don't want to put any apparatus. I am not doing any experiment. I'm just letting the system freely evolve there. And this corresponds to a special probe, which is called the null probe. So this is the symbol here for the null probe. So it just means you let the system freely evolve there. Okay, so now let's come to the black hole to white hole transition example. Okay, so in this diagram there are already a lot of things. So let me explain this slowly. So the first thing I should say is this model isn't really about making realistic physical predictions. It's the reason I put it here is really as a conceptual example to see the application of the positive formalism in a context where other traditional approaches to quantum gravity, let's say, fail. Okay, and fail for different reasons. But so let me first say a little bit more about this diagram. So the physical situation is the following. You have, so this is supposed to be a Penrose diagram. Okay, so here your you can think of this of an axis in space-time. Sorry, a point in space-time, a center, which is corresponding to the left line here as a point in space, and you extend it over time. So this is this axis here on the left. Now you think of this as, so let's say you're first in Minkowski space, and then suddenly there's a shell, a thin shell of matter, so a spherical configuration of matter that's collapsing. Okay, so this is in the diagram. This is this red line here. So collapsing means it moves to the center, and time goes upwards here. So it moves towards the center. And moreover, we think that this is what happens at the speed of light. So it collapses. And then, of course, what will happen is, well, this will form a black hole, right? So this would form a black hole. And usually in classical GR, what happens? Well, we form this black hole. There's a singularity at the center. And this black hole will just now stay there, basically. Now, there are some ideas motivated from quantum gravity that would say what should happen is that the singularity in the center is not really a physical. So, I mean, it signals that general relativity breaks down. And so in some sense, there shouldn't be a singularity. And I mean, there shouldn't even be a well-defined notion of classical space-time in the interior. So one thing that could happen would be that there's a kind of bounce, okay, so that the matter comes in, but what really happens when it's really near the center is that by some quantum tunneling process, it explodes essentially, and the matter is thrown out again. And this is this black hole. So when the matter comes out, in a way, time symmetric to the matter coming in initially, forming the black hole, then this is called a white hole. So a white hole is basically a time reversed black hole. So this motivates thinking that there might be a transition from a black hole to a white hole. And so the matter comes out again later. Now this is an extremely simplified model. So it's spherical symmetric, and you just have this shell that moves in at the speed of light, and then at a later time, this the material is ejected again, and of course there's no classical solution of GR that admits this. As I said already, classical GR, the black hole would stay forever. So what you suppose is that you're saying, okay, so there's no classical space-time metric near the singularity. Something quantum happens, and later this material comes out again. Now, what's important is that, so how is this physically characterized? Well, there's really only just one parameter, which is the mass of this shell that moves in. Okay. We're just in Minkowski space. There's this shell that moves in, and there's just one parameter, which is the mass. Now, it turns out that if you cut out this interior part of the metric and just look at the metric in the exterior, and you say, okay, so here before this moves in and after the shell comes back, I should be in Minkowski space. Then it turns out there's, for each mass, again, a one parameter family of solutions of general relativity in the exterior. So that there is a classical spacetime in the exterior. So this is this orange region without this kind of bluish part in the middle. And so what happens is that it's a one parameter family. And how is it characterized? It's characterized by what's called the bounce time. So you can think of this as if this shell comes in and it's sitting at the center, and then you're waiting for a certain time, and then it comes out again. And so basically you have this freedom to choose this time. So there's this family of solutions in the exterior that, so you have two parameters, the mass and the bounce time. And so how can you measure the bounce time? You measure it by some observer that's removed from the center. So the observer just sits there and sees suddenly this mass shell comes by and moves in. And then the observer starts his clock, and at some later time, the mass comes, the shell comes back, and the observer stops the clock. Now the time the observer sees on the clock doesn't correspond directly to the bounce time. The observer has to do some GR calculations to extrapolate if there was a solution of GR here, how much time would have evolved, okay? But the observer can do this calculation. So basically, doing this, the observer can basically directly observe this bounce time. Now, to describe this with traditional approaches to quantum gravity, unfortunately, I don't have as much time to go into why this is a big problem. Let me just quickly mention that, so for example, in the canonical approach, you would have to think of, you can think of, for example, quantum geometric dynamics or the traditional loop quantum gravity. You have your data corresponds, your Hilbert space corresponds to what happens on a space-like hypersurface and how things evolve there. But of course, if you have a black hole, then there's a singularity, and you don't have space-like hypersurfaces that describe the interior of the black hole. I mean, that's just doesn't work. Now, if you are thinking about an S-matrix approach, so a scattering approach, so you're thinking of the observer sitting there, and I mean, the traditional S-matrix approach is you throw in some particles and you wait and you see what comes out. So here, the only thing that's thrown in and comes out is this mass shell. Now, the problem is that this bounce time doesn't correspond to seeing any different particles coming out and looking at their different quantum numbers and so on. What comes out is the same what comes in, and for each bounce time, what comes out is the same. So in some sense, the scattering matrix that compares initial thrown in stuff with final thrown out stuff cannot see the bounce time. So you have, in fact, you have this one parameter family of bounce times that asymptotically changes your space-time by time translations. So in other words, the point is that there's no asymptotically fixed space-time, but the bounce time itself can be felt arbitrarily far away from the black. So an S-matrix, which also relies on a perturbation around a fixed classical space-time, this perturbation doesn't go away when you move away from the black hole, but this time difference stays constant when you go to infinity. So the S-matrix also doesn't work. Okay, so how does the positive formalism approach this? Okay, so we have three regions of space-time, two regions, the exterior, which is well described by classical GR, X, and the interior, which you would think, okay, there I need a quantum theory of gravity to describe this. This is Q, and sigma is a hypersurface I put here, which is the interface between these two regions, between X and Q. Now, what are the probes that enter here? Well, there are just two space-time regions. We just have two probes. One probe, which is the one corresponding to what happens in the quantum gravity region in the interior. This is, well, it's you need this quantum theory of gravity, but the probe is just the probe that I previously told you is called the null probe, that just corresponds to the quantum system doing its thing, there not being any measurement or intervention on your part. So the measurement is taking place in the exterior region in X. And so basically the probe So since we just have two parameters, they are also reflected in the probe. And we can see this here more precisely. So basically a question then you can ask that would be typical would be saying, okay, I fix the shell mass, and now I want the probability for this shell mass that the bounce time lies in a certain interval, let's say tau1, tau2. Okay, so I've indicated this pictorially in this way by two pointer devices, one for the mass and the other one really showing here a range of possible pointer outcomes. So so this probe corresponds to all possible pointer outcomes in this interval, tau1, tau2, and to a fixed mass m here. And so what we have to calculate is basically what are these probes, and of course what's the state space corresponding to the interface sigma, and then compose these two probes, and this will give us a real number. But we need another real number, because we have to compare this to the real number we get if we consider, because what we're doing is we are fixing the mass. So that's something known that corresponds on my previous slide to the right-hand side here. There's something that's on the right-hand side that's fixed. But what we do not fix is the bounce time. So the bounce time here corresponds to the interval of all possible bounce times. So these are here taken to be positive, and the mass, of course, is also positive. So these are two numbers between 0 and infinity. Okay, so the probability for the bounce time to be in this interval is this quotient. Okay, now first let me, and there's a paper that where this is explained to some extent. So let me first suppose that we have a classical theory, so that there's, let's say, a modification of general relativity or something that in fact does allow me to continue the metric to all of the interior of the region Q. Okay, so having a classical theory means now that the partially ordered vector space that we assign to sigma is, as I told you before, is just the space of functions on phase space. So we need first the phase space. What's the phase space here? Well, the model is extremely simple. We just have two parameters, the mass and the bounce time. So it's just the space of these parameters. So if you want, it's R plus cross R plus. Okay, that's just two. And this also coincides with the space of solutions of the equations of motion in X here, because I mean, that's how we have set it up. We said, okay, we have solutions in the exterior determined by these two parameters. So here, this is the phase space associated to the hypersurface sigma. Now in Q, so since we have now this classical theory suddenly, that means that we'll have one solution in Q. So for each shell mass, there will be one solution, which means in particular that from this solution, I can then extract the bounce time. So there's also one bounce time, which is the actual physical bounce time that occurs if the shell mass is M. So here we have a subspace of the phase space, which is the pairs of mass and bounce time that are compatible with the classical solutions here in Q. So it's this subset. Okay, so as I told you already, the statistical phase space here on sigma is the space of functions on the phase space, and the inner product is just the integral over the product of functions. Here we are just choosing the usually back measure dm d tau on this phase space. Now the spaces of probes, since these probes will pair with one another through this state space on the hypersurface, they will be so the pairing is such that the spaces of probes, we can either take them to be the same as this SB sigma or the dual space. If we take them to be the same, then for the pairing, we have to use the inner product, or we can choose one of them to be in the dual space and one in the space of functions itself, space of statistical functions. So the positive formalism here doesn't exactly tell you which way you have to do it. You have some freedom to do it, but this freedom doesn't have to do any bearing on the physics. It's just some choices of mathematics which are more convenient to you, and of course the result doesn't depend on this choice. And so the null probe enforces the classical bounce time, which means that we choose it here to be dual to statistical distribution. So if I plug in a statistical distribution, this will correspond to integrating with a delta function where the bounce time is enforced to be the physical bounce time, which results simply in an integral, which is only over the masses where I insert, where I insert the bounce time here. Now the probes that correspond to the measurement so the one where we don't specify the bounce time is not just the delta function that enforces the specific shell mass that we fix. We call this M0 here. And if at the same time we restrict the bounce time to be in an interval, that would just correspond to multiplying with the characteristic function for this interval of the bounce time. And now you can just plug in these functions into this formula here. So the pairing between these probes is now just consists of inserting these functions into this functional here. Okay, so if you do that and you take the quotient as specified here, then what you get is simply, you get this expression. So the probability at shell mass M0 for the bounce time to be in the interval tau 1 to 2 is either 1 or 0, right? Because there's a specific bounce time. And if this bounce time, this classical bounce time lies in the interval, you get 1. And if it doesn't, you get 0. So that's exactly what you expect to get. Okay, now.
Robert?
Yes?
A question.
Yes.
Thank you. I have a basic question. So the probe, the observer, is covering the classical part of the space-time, and the bounce part is genuinely quantum. Is that possible that for the probe, you are measuring the same bouncing time, but what really happened in the quantum region, you probably have a superposition or different eigenvalues. So then the observer wouldn't be able to detect from traveling along a geodesic outside of the region.
Okay, sorry if that wasn't clear. So first I told you, when I told you about this, the problem, I was saying, okay, so here we have a quantum region where there's quantum gravity. But now I'm revising my assumptions just for illustrative purposes. And I'm supposing that, in fact, there is a classical model. Okay, that there is a classical bounce.
Okay, I see.
So this is my, I'm sorry that, yeah, maybe I should have set up things slightly differently, but so for the moment, we're supposing there's a classical bounce.
Okay, I see.
And yeah, so that means that we have this classical bounce time for each shell mass, we have a classical bounce time, and then the probability is 0 or 1, depending on whether this classical bounce time, of course, is in the interval that we are asking about or not. So of course, you could have immediately told me that this formula was the answer in this classical, supposed classical situation, classical solution. But what I wanted to show you, of course, here is that the positive formalism reproduces exactly the correct answer, but in the conceptual setting of its own. right? Where we really talk about these probes, the way they are composed, the probability that are extracted. And so just to show you, you indeed get the correct probability. And in fact, more generally, it is easy to see that the positive formalism in the classical setting, that this quotient I told you about is the correct answer in the classical setting. So basically, there's no doubt about this. But here, this is I'm just showing this at the example. Now, of course, what we want is to think about the situation where the interior region is not, there's no classical solution there, and indeed it has to be described by quantum theory. So we come to this situation now. In that case, of course, instead of the classical phase space, we have a Hilbert space of states on this hypersurface, which is mediates between these two regions. And then the space of self-adjoint operators on the Hilbert space is the space of mixed states that we associate with sigma. And so this is the partially ordered vector space that we need. And of course, the density matrices are the positive operators in this space. So the positive elements in this partially ordered vector space. Now, okay, we have a description in terms of classical parameters. So how do we link this to quantum theory? So we will suppose that in this quantum theory, we have coherent states labeled by the bounce, the shell mass and the bounce. Okay, so these are now states in our Hilbert space that we think of as approximately describing the classical geometries in X and corresponding to a given shell mass and bounce times. So it's crucial here that for this to make sense, we need a completeness relation. So so the coherent states will an integral over the coherent states in this way will give us the identity in the Hilbert space. So this is, I should say, something natural in many constructions of coherent states. So for example, Perelomov coherent states would naturally satisfy a property like this. Now, the interesting thing about this is that at the same time, we can interpret this completeness relation as a positive operator valued measure. So that means if we, so our classical phase space is this two-dimensional phase space labeled by shell mass and bounce time. And if we take a set in this space and integrate with this integral, then we get an operator, a positive operator that would correspond to, so usually you think of positive operator value measured as making a measurement. So measuring that your state is in some part of the phase space. Now here, there's also measurement, but it's not that you first have the state and then you measure it. So the perspective is a bit different, but mathematically speaking, this is exactly the same thing. And also the physical interpretation is very close to the usual interpretation of positive operator valued measures. So if you have a statistical distribution on phase space and you plug it into this formula, then you get a positive operator, and you think of this operator as encoding this classical function in the quantum series. So more specifically, if this function is a characteristic function for a subset, then you think of this operator as representing in the quantum theory the situation that you are in this subspace of your classical phase space. So it interfaces between classical and quantum theory. So in this way, in particular, we can construct the operators in the quantum theory that correspond to these measurements which involve bounce, shell mass and bounce time. as positive operators on the Hilbert space. So the functions that we put into this formula that we quantize, to say it like this, are, however, exactly the same that we had on the previous slide. Okay, so this is exactly these functions here that from the classical theory that we have to plug in to obtain the corresponding quantized operators that represent these in the exterior region and on the hypersurface sigma. So this is the exterior region where we have these coherent states that allow us to interface between the original classical description and the quantum description. Now, in the interior region, as I said, we're just looking for the null probe. So this is so now we think of this again as an element in B sigma star. So B sigma now is the space of density matrices, if you want, or self-adjoint operators, and the density matrices are the positive cone. We can think of this as a map from those to the real numbers. And now this map is just given by the amplitude map of your quantum theory. So the amplitude map in the general boundary formulation that is a map from the Hilbert space on the boundary to the complex numbers. And then you can use this formula to convert this to the corresponding null. Now, this formula might seem to fall out of the sky. And if there's some time later or somebody asks a question, I can explain more in detail where it comes from, and that it's something very natural and reduces in the standard formulation of quantum theory to exactly what you would expect it to be. I will just say that the use of coherent states here is only for convenience, and I could also insert a complete basis of the Hilbert space. But since I already have these coherent states that give me a completeness relation, I will use them, and that will be beneficial because once I pair this this probe, this null probe with the probe that does the measurement, then this allows me to evaluate this in an easy way. So, so on the right-hand side, as I said, I'm using this to insert a function on the classical phase space, convert this to a quantum operator. So if I combine this with this probe, so this probe will be applied to the quantum operator that comes out here. Okay, so just combining these two integrals and simplifying the expression gives me the following expression. Okay, so now we have this classical phase space function on the that corresponds, that allows me to encode the measurements in X. And here we have the amplitude of the quantum theory in Q on the coherent states. And this is the pairing between the two. So that means that now the bounce time is just this expression, a quotient with this expression in the numerator and in the denominator, where in the numerator, I plug in what I told you before, this function, this function here. And in the denominator, I plug in this function here. And then I can simplify the result in such a way that I obtain this expression here of moduli of the amplitude map on coherent states. So this is the answer. Of course, as I told you, the positive formalism does not tell you what the quantum theory is that you're using, in the same way as quantum theory as such doesn't tell you what's the concrete quantum theory you should use to model something. And so it just tells you that if you have a quantum theory in Q, this is exactly the way how you can use it to extract the probability for the bounce time to lie in a certain interval given a fixed shell mass. Okay. So yeah, so I think I used already a bit more than an hour, or maybe an hour. So I think I should stop here and yeah, look forward to your questions. Thanks.
Thank you very much. So I would ask if anybody has a question, come closer to pose. Yeah, please.
I have a clarification question. So the physical meaning of this probability is that you already assume deterministically that this black or white hole transition will happen, and what is the final state we already know, and the probability is just about the transition time.
Yes, yes. So I'm assuming, so as I said, this model is extremely simple and just has two parameters. And so it's not really something that we'd expect to be realistic. And also, so there are two aspects. So one is that we just have these two parameters. And of course, the other aspect is that I have not told you, I have not given you some specific quantum theory in the interior that would give you some concrete prediction, right? So of course you can. I mean, also I'm very doubtful about if this so much simplified model really has physical relevance. But I think it's interesting as a kind of paradigma of how, in principle, we can talk about probabilities in contexts that, for example, involve black holes and their evolution, or more generally, quantum gravitational contexts.
Any other question? I would have a question. I'm interested, yeah, then we'll let somebody online as well. I would be interested in if you are able to pinpoint what is this particular feature of this example, why other models, other approaches will not be able to capture. You mentioned at the beginning, for example, the S matrix and the impossibility of having asymptotic states. But some work has been done recently in the Fuster group in York of how you can make and model measurements in the quantum field theory that are not of the asymptotic type and S matrices. So I feel there is a lot to be done there and to characterize these local operations, but that this still is a part of the conventional approach, if I may say that. So I'm wondering, can you say what kind of situations we can imagine such that the positive formalism is more general and the only possibility to deal with this situation as compared with the more conventional approaches?
Yeah, so I mean, I really think that this example, this is in fact an example of that. So I don't know how you could use algebraic quantum field theory to predict something like this. I'm quite doubtful about this, frankly, but I don't know this recent work that you're talking about. So, but in algebraic quantum field theory, I mean, first of all, it's not about, it just works with fixed metric backgrounds. I mean, it's about quantum field theory in curved space-time. And so the problem here, I mean, okay, of course, there's no metric in the interior here. So at least algebraic quantum field theory will not be able to, even in principle, to address this question, what is the quantum theory here? Okay, that's one thing. And the other point about this example is that so the way to understand the space-time in the exterior is that even for a fixed mass, you have this one parameter family of solutions. And you cannot distinguish these solutions by looking at stuff that goes in and that comes out. You can only distinguish them by looking at the modification of the asymptotic structure of spacetime due to the model. So if you change the bounce time, you change asymptotically the structure of spacetime, not by introducing curvature or something, but by expanding it by constant time. So I don't know any other way that you can detect this constant time in a conventional scattering type QFT approach. But yeah, maybe I'm not imaginative enough, and I'm sure people have thought about this and maybe came up with good ideas recently. I don't know.
But can you generalize and make a statement? What is then, independently of this specific example, what is this feature that needs to be there in such that at least we don't know whether a conventional approach will work, but the positive formalism would work? You talk about, is this some, I mean, I mentioned this asymptotic states, but I don't know whether this is the one or.
Yeah, okay, so I mean, okay, so algebraic quantum field theory is a bit problematic for other reasons that I don't want to go into. But let's say we are limiting ourselves to approaches that adhere to the standard formulation of quantum theory. Okay, so if we do that, then in this example, the problem is that we don't have a temporal order between these two probes. So, okay, yeah, there are some things that I would have said if I had more time about how you specialize to the standard formulation of quantum theory and the additional axioms that come in, and which are axioms that in particular allow you to simplify the formulas for probabilities and get, at least in special cases, linear probability formulas, but these break down in the moment where you don't have this fixed temporal order. So the positive formalism gives you a means to talk about probabilities outside of this case of a fixed temporal order. Of course, if you have a fixed temporal order and you apply the usual normalizations, then it just reproduces the standard formulation. But I think, I mean, this in particular here is an example where this is not the case. So for example, you cannot, the result that you get here, if you look at this quotient, you cannot ignore the denominator here. I mean, this will not be a quantity that's one. So you cannot apply a linear probability formula to get the result. So there's no way that you can express this directly within the standard formulation of quantum theory. Yeah. Okay, I'm not sure if that goes towards answering what you're asking.
I think it's going in the direction I asked. Yeah. So there was an online question. Would you like to pose the question? Graffer, I see here.
Yes. So do I correctly understand that? So with your formalism, you show that by just looking at the bounce time, it is not possible to distinguish whether we are seeing a quantum gravity effect or some classical deviation from Einstein gravity.
Well, one difference that you would see is that in the quantum case, this probability will be some distribution, whereas in the classical case, the probability will just be a characteristic function, because there will be one physical bounce time, So if you make observations and you see that for a given shell mass, you always get the same bounce time and not some distribution, then basically you can say that looks like a classical solution, that there's a classical dynamics at work. Whereas if you see a distribution, then you would say, okay, this has to be a quantum phenomenon. So that's the only thing that I can. But of course, that's not something that's specific to using the positive formalism. I mean, it's just something that you would physically expect, right? I mean, in a classical theory, there would just be one bounce time, and you would expect, obviously, in the quantum theory, that there would be distribution. So that's not what the positive formalism does. Is only it tells you how you can calculate this distribution given the ingredients, the basic structure of your quantum theory. That's what it does.
I see. So you would have to really do the experiment repeatedly and see whether this is a probability distribution.
Right.
Okay, so I think we are quite extended in time. I would have a lot of questions, but we can do it over email. I would like to thank you for the presentation and everybody else online. Bye.
Thank you for inviting me. It was a pleasure. Yeah, and please feel free to send follow-up questions.
Yeah, thanks.
Amen. Okay.
So.